Hey guys, welcome to our last video of the year. This video, 6.3, is on complex momentum problems. Complex is probably not the best word to use. We're really just focusing on momentum problems. It seems maybe a little bit more complex than before, but our previous video was just about conceptually about momentum being conserved, and this video is going to be focused more on the math behind it. So one of the formulas we learned in our previous video is that the momentum before a collision is going to be the same momentum after the collision. And this is really the total momentum, right? So if I was to break this down even further, how do I find out the total momentum before the collision? Well, total momentum is always going to be the momentum of every single object added together. ... So there's only two objects. So you take the momentum from the first object and add it to the momentum of the second object, and that will be the momentum, before. Then you look at the momentum of the first object after the collision and add it to the momentum of the second object after the collision. And then they should equal each other. So to break this down even more, how do we find momentum of an object? It's always the mass of the object times the velocity. Now, velocity is a vector quantity. Okay, it'll either be positive or negative. Positive is if it's going in, this direction, and then negative is as if it's going in this direction. So the direction is important. It's going to impact the sign of your momentums. So this is the formula we're going to be using to solve these problems. So I'm going to do, I think, 3 example problems with you. So example 1, a 15 kilogram medicine ball is thrown at a velocity of 20 kilometers per hour to a 60 kilogram person who is at rest on ice. The person catches the ball and subsequently slides with the ball across the ice. Determine the velocity of the person and ball after the collision. So this is normally what you're going to see on your test. You're not going to be given the picture below. So what we need to do is we need to learn how to read this and then draw this picture. So first thing is always have a before drawing and an after drawing. Okay, so let's label everything we know before. We know that a medicine ball weighs 15 kilograms. So my medicine ball has a mass of 15 kilograms. You can write that in both the before and the after because the mass of the medicine ball is not going to ever change, right? So we put the mass for the medicine ball on both sides. Then we keep reading. It says the medicine ball is thrown with this speed. So that's the speed before the collision, okay? So when the person catches the ball, that's the collision. So it's going at a speed of 20 miles per hour. So here's my velocity and here's my mass, okay? So this is the medicine ball before. Then we have the person before. The person, it says, has a mass of 60 kilograms. That's not going to change. So the person, here's his mass. So we're also going to put that on the after because the person's mass is not going to change, okay? And it says the person is at rest. That means that their velocity is 0. So that's what we put here. Velocity is 0. So we have the mass and the velocity of the medicine ball before. So we could take these and we could calculate the momentum of the medicine ball. Think of this as momentum 1. This is the first object. This is our second object. So we could also take these two and we could calculate the momentum of our second object. This is all before. So basically what we're doing is we're solving this part of our problem. This is the before. But the second part of our problem is to find the momentums of our objects afterward. So let's start by writing out this problem here. The way I could write it out is I could say my momentum of object 1 and my momentum of object 2 before should equal the momentum of object 1 and the momentum of object 2 after. Okay. So what's the momentum of object 1 before? Well, here's object 1 and here's the information. So to find this, I have to do mass 1 times velocity 1. So basically I'm taking my 15 and I'm multiplying it by 20. So we're going to do that on our calculator, and someone left their calculator here, so I'm going to use it. And it's 300. This is momentum, so my unit is kilograms times meter per second. Now let's find the momentum before of object 2. So the mass of object 2 times the speed of object 2. So the mass of object 2 is 60 times the speed of object 2. So 60 times 0, what's that going to be? It's going to be 0. There's no momentum. That should make sense, guys, because if an object's not moving, there's never momentum. So do you see how these are being added together here? I want to be sure I add them together. So 300 plus 0 is 300. So that is my momentum before. Okay, this is my before. It's my total momentum before. We know that's going to equal the total momentum after. So let's calculate that. What's our total momentum after? Well, we have to add the momentums of both of our objects after. So let's figure that out. So the momentum of object 1 after should be the mass of object 1 times the velocity of object 1. We have the mass of object 1, but do we have the velocity of object 1? No, we don't. We don't have that. So I'm going to write 15 times v. That's the velocity of object 1. Okay. Next, let's do our momentum of object 2. It should be the mass of object 2 times the velocity of object 2. Remember, all of this is after the collision. So the mass of object 2 is still 60. And we don't have the velocity, so I have to put v right here. Okay, so now let's look at our equation. We have 15 times v1 plus 60 times v2. And it equals 300. Okay, so what do we do next? Well, if you look at the picture, it tells us something really important. The objects here are combined. The medicine ball is touching the person and they're staying together. They're connected. That's really important. What that tells us is since the objects are connected, their velocities are the same. So instead of writing v1 and v2, I'm just going to write v. Okay? So now that I have just v here, I have 15v plus 60v. We can do algebra to get the v out. So I'm going to factor out the v. So I have 15 plus 60, which becomes 75. Okay? Now on the other side, this whole time, we've had 300. So now I do 300. I'll divide by 75, and that gets me v. So if I take 300 and divide it by 75, I get 4. So my velocity after the collision was 4 meters per second. Okay. So it's really important that you list everything before and after. So let's go ahead and do that with example 2. Okay. So we're reading this situation, and remember, we have to start by labeling everything. So a 0.15 kilogram baseball moves at this speed. So I write it right here. This is the mass of the baseball. Here's the speed of the baseball. And I'm going to label it. Baseball before. This is going to be object 1. The person's going to be object 2. So baseball is object 1. So if I wanted to find the momentum of object 1 before, I multiply these two together. Right? Okay, now I'm going to look and keep reading. I strike a mitt that weighs this much. It's at rest. So I write that down here. Here's the mass of the mitt. Here's the speed of the mitt. Okay, this is my mitt. It's object 2. I could multiply these together to get P2 before. So start by finding what your momentum is before. Remember, momentum before equals momentum after. So my momentum before, let me take it over here. Momentum before is momentum after. How do you find momentum before? You add together the momentums of the objects before. So object 1 has a velocity of 45 and a mass of 0.15. Object 2 has a mass of 0.25 and a velocity of 0. What does this come out to? Well, 0.15 times 45 is 6.75 plus, and this is 0. So I get 6.75. That's my momentum before. It should equal my momentum after. So the momentum after is found by finding the momentum of object 1 and the momentum of object 2 after. So here's object 1, the baseball. Here's object 2. And if you read the problem, it will tell you the catcher's mitt immediately recoils backward at the same speed as the ball. So that means they're together, they're combined. So my speeds here, there's no V1 or V2, it's just V. They both have the same speed, okay? I keep reading. The catcher's hand is at a relaxed state at the time of collision. It can be assumed there's no external forces to determine the post-collision velocity. We want to find this, the velocity after the collision. Okay, we're already given these masses from the beginning of the problem. Mass never changes, so you don't have to look for it in the problem because it's already there. So my mass of object 1 is still 0.15. I don't know the velocity, so I'm going to put V. My object 2, the mass is still 0.25 times its velocity, which is V. I didn't label V1 or V2. I just labeled them both V because they have the same velocity. So next, I'm going to combine them so it looks like this. Now I want to take the V out, so it's 0.15 plus 0.25. So now I'm going to continue. I'm going to add these two together. So my V now equals 0.40. So to find my velocity, I do this. So I'm going to put 6.75 divided by 0.4. My velocity is 16.875. And what's my units? Well, it's always going to be the same unit as what you were given. So we had meters per second here, so it's meters per second. Okay. Let's do one more problem. This one's a little different. If we read this problem here, remember we always label everything before and after. So we have a 3,000 kilogram truck, so we label that here. With a velocity of 10 meters, so we label that here. And then you need to label this is your truck. This is P1. Okay. Your truck is also, you're going to write it down here after as well. Here's your truck. Still P1. We keep reading. It hits a 1,000 kilogram parked car. Okay. The impact causes the car to be set in motion at 15 meters per second. So I pause here. It said it hits a parked car. What does the parked mean? Parked means it's not moving. So P2, or my car, has a mass of 1,000 and a velocity of 0. All that's before. The impact, that means that that's the collision. So everything before this was before. Everything after the collision is after. So let's keep reading. It says now the car is having a speed of 15 meters per second. So I list that right here, 15 meters per second. I'm using the same mass as before because mass never changes. So let's look at what we're given here. We are given everything except for our velocity afterward of the truck. So it wants to know what's the speed of the truck after it hits the car. Well, let's create our problem. P before equals P after. Let's break P before into P1 and P2. Let's break P after into P1 and P2. If I was to break that down even more, this is the mass and velocity of object 1. P2 is the mass and velocity of object 2. And this is the same thing. But remember that this is all before and this is all after. So let's plug in all of our numbers, okay? So what is the mass before of object 1? Well, it's 3,000. What's the velocity of object 1 before? 10 meters per second. Okay. What's the mass of object 2? 1,000. What's the velocity? It's 0. Now let's look after. So we're looking over here. The mass is the same. It never changes. So here's 3,000. But the speed now we don't know. Actually, I'm going to change that to v. We don't know what that is. Okay. And over here we have mass, which doesn't change. And we have the velocity. And it actually gives us that velocity, which is cool. Why does it have to give us that velocity, by the way? So remember how we talked about, oh, the velocities are the same. Well, why are the velocities not equal here? Well, the reason why they're not equal to each other is because they're not connected. When this truck hits this car, they bounce, okay? The car moves forward, and this truck will actually, it doesn't technically move backward, but it's going to move slower forward. So there's actually a gap here. So it's like when this guy hits this guy, and then he still keeps going forward. So that's what's happening. So these velocities are not the same because they're not connected, okay? If you have a collision where they're connected, then the velocities are the same after. So now once we solve this, we're going to get 30,000 here plus 0 equals 3,000 v plus 1,500. Okay. So our next job is to solve for v. So this is really just 30,000. I want to move the 15,000 to the other side. So this becomes 15,000. I want to get rid of the 3,000, so it's just v. Okay. And so then it actually just becomes 5. Our velocity after for the truck is 5 meters per second. So you can kind of tell what happens. He was moving at 10 meters per second and see how he slowed down to 5 meters per second. Just let's talk a little bit about conceptually what's happening here. This truck has a certain momentum. After it hits the car, what happens to its momentum? Well, you should know the momentum slows down, right? So this momentum was high. After it hit the car, the momentum slowed down. What did we learn about the conservation of momentum? Well, it has to be the same. So if the truck lost momentum, that means the car must have gained momentum. How much momentum does the car have at the beginning? 0, right? It's 0 because it's not moving. But afterward, it has higher momentum because it got hit. So momentum got transferred here. And I was using m, but really I should have been using p to describe m. Because remember, momentum is p, it's not m, because we're going to get that confused with mass. So it's important to remember. Now they both had the exact same change in momentum. Their change in momentum is exactly the same and their forces are exactly the same. It's just that this car accelerates greater because it has less mass, and the truck accelerates less because it has less mass. So actually, I lied. I said that was one more problem. This is our last problem. But, you know, the more practice problems I do with you, the easier it is for you to do this on your own. So, okay, a railroad diesel engine has 5 times the mass of a boxcar. What that means is I'm going to say my object 1 has a mass of 5, and my object 2 has a mass of 1, because it's 5 times more, right? So what I'm doing here is my train is going to have a mass of 5, and my boxcar is going to have a mass of 1. Okay. So really, we're going to say mass is 5, mass is 1. Okay. We keep reading, and it says the diesel, that's the engine, has a velocity of negative 4 meters per second because it's going backwards. So this really should be a negative here, negative 4 meters per second. But our boxcar here is at rest. So all of that's before. All of this is before. So this is P1, this is P2 before. Now after, here's P1, here's P2. Afterward, they have this same mass on both of them. So this guy's mass is 5, and this guy's mass is 1. But we want to find out what their velocity is. It's the same type of problem. Their velocity is going to be the same. They're equal. Why? Because they're connected. So I can do my same problem. This is before. This is after. Okay. So remember, m times v just stands for p. So m1 v1 really stands for p1. Okay, so I could have written it like this too. p1 plus p2 equals p1 plus p2. But remember, these are p1 and p2 after, and this is p1 and p2 before. So you should be able to solve this problem because it's asking for how fast do the two train cars move. So train car 1 has a mass of 5, a velocity of 4. Train car 2 is at rest, so I know its momentum is 0. I just did 1 times 0, so I got 0. The momentum of the car after, has a mass of 5, but we don't know the velocity. And our second object has a mass of 1, and we don't know the velocity, but we know the velocities are the same. So when I solve this out, okay, I do 5 times 4 plus 0, and I get 20. Okay, when I do this, I get 5v plus 1v. Okay, let's take out the v, so we get 5 plus 1. Okay, that's basically 6, obviously. Let's change that to 6. So then we get rid of the 6. So 20 divided by 6 is going to give me my velocity, which is 3.33. And they gave us in meters per second. So that's our answer, meters per second. And that's it for our 6.3 video. It's basically the same type of problem, and I just did a bunch of examples. So your practice problems, you have 2. The first one does not have a diagram, so you need to draw the diagram. You need to label everything. The second problem does give you a diagram, but not everything is labeled. So you still need to label like your mass and your velocity of each object before and after, and then show all your work. And that's it. See you later, alligator.